Design analysis and optimization of an all-terrain vehicle, ATV. Designing frame, knuckle, and suspension arms. Abstract. The paper summarizes the steps taken in finalizing the design of an electric ATV, made for SAE BAJA, which provides a platform for undergraduate students to apply the principles of engineering to expose their proficiency in the automotive world. The purpose of the paper is to calculate various boundary conditions on the frame, steering knuckle, suspension arms of a light ATV under extreme conditions and use them to improve the overall design, which requires the minimum amount of material while providing a significant factor of safety. An iterative approach using standard calculations and FIA is discussed in the study for simulation and optimization of the design. For all parts, stress and deformation analysis is performed. For design optimization in the knuckle, topology is done. Von Mises stress, total deformation, and safety factor were calculated for each part under appropriate boundary conditions. The study discussed step-by-step calculations of forces on each component in detail and their simulations with an appropriate degree of precision. Following the methodology shown in the study will be useful in the development of a light ATV. Further, the suggested simulations will ensure the safety of the vehicle. Keywords: von Mises stress, deformation, safety factor, design, material selections, FIA, topology, knuckle, frame, suspension arms. Introduction. As the name suggests, an ATV is a vehicle that runs on tough terrains, and hence every part of the vehicle was designed such that it can successfully withstand different types of loadings in off-road conditions without having any permanent deformation in it, i.e., von Mises stress value in the analysis should be very much lower than the yield stress of the material. All the parts of the vehicle are designed in SolidWorks 2018 and analyzed in ANSI 19.2 with extreme boundary conditions, and for setting up the steering and suspension geometry Lotus Shark was used. 2. Research gap. A detailed calculation of boundary conditions and stepwise approach to design the parts of a light ATV which can withstand extreme loads was needed so that one can find a complete study in one paper. Further, current publications either fail to take all the required forces in consideration or fail to explain their calculations. 3. Methodology. Finalizing the design was an iterative process. Steps included in the process: 1. Preparation of basic design. 2. Calculation of boundary conditions. 3. Analysis of the design under calculated boundary conditions using the finite element method in ANSI software. 4. Optimization of design based on results obtained from the analysis. 5. Again, applying step 3 and 4 on optimized design. 6. Repeating the process to get the desired design. 4. Frame. The frame is a structure made up of metal tubes whose main objective is to ensure the safety of the driver and carry different components of the vehicle such as powertrain, steering and suspension, etc. The design process of the frame can be divided into 4 steps. 1. Material and cross-section selection. 2. Designing the roll cage according to the rule book. 3. Analysis of the roll cage with calculated boundary conditions. 4. Ergonomics check using PVC pipes. A. Material and cross-section selection. After considering each parameter like strength, weight, stiffness, cost, availability, and a detailed market survey, we shortlisted 2 AISI graded materials which were fulfilling the requirements. First one was AISI 1018 steel and the second one was AISI 4130 steel. The details of both, as provided by the dealer, are given in the below table. We can see AISI 4130 provides good strength, but at the same time it is costlier than AISI 1018 and has poor weldability, and also after considering the fabrication constraints like available welding method, we used SMA, availability of the material in local market, and total cost. We selected AISI 1018 steel as our primary and secondary material because it is cheap, easily available, can be welded by SMA, and it also provides sufficient bending strength and bending stiffness to overcome the constraints for primary material as given in the rulebook. The cross-section was selected after calculating bending strength and bending stiffness of primary material, and the calculated figures are as below. Material used, AISI 1018. Yield strength, SY, 418.82 MPa. Young's modulus of elasticity, E, 205 GPa. Outer diameter, DU, 25.4 mm. Inner diameter, D, 19.4 mm, thickness equals 3 mm. Second moment of area, I, 13,478.64 mm4. Distance from central axis, C, 12.7 mm. Calculated bending strength, 444.497 MPa. Calculated bending stiffness, 2763.121 Nm2. We can see that bending strength and bending stiffness is exceeding the minimum required value, i.e. 387.377 MPa and 2763.121 Nm2. So, the cross-section of primary material was decided to be 1 inch outer diameter and 3 mm thickness, and that of secondary material to be 1 inch outer diameter and 2 mm thickness. B. Designing of roll cage. The design process of the roll cage was iterative and based on several engineering and reverse engineering processes. Firstly, we decided the driver of the vehicle according to weight and height, and then took every required measurement to start the designing process of the roll cage in SolidWorks 2018. During the designing, we took care of each rule given in the rule book, the driver ergonomics, and also the requirements of various domains. In this way, we prepared a basic model of our roll cage, and we used Kasha V5 to prepare a driver mannequin and checked for required clearances for the driver. Now the only thing we had to do was certain modifications based on the analysis. After these modifications, we got the final design of the frame. See finite element analysis, FIA. The roll cage is made up of circular pipes with hollow sections, and thus we can neglect the thickness of the pipe, and the pipe can be assumed as a curved rectangular surface, so we have used 2D elements for meshing the roll cage. The method used was quadrilateral dominant. We tried both the first order and second order elements but didn't find any significant difference in the results, so after considering the time and hardware constraints, we used first order elements. We also did the mesh dependency test, grid independence, for different element sizes and found the saturation around 3 mm as shown in the figure. We have used the appropriate value of proximity for the joints, as they are the areas of high stress concentration. The boundary conditions were considered such that they satisfy the actual dynamic loading conditions in static structural. We have considered two types of impact forces. One, impact of roll cage with a rigid body, like rock, wall, impulsive time of impact equals 0.15 seconds. 2, impact of roll cage with a deformable body, like a tree, another roll cage impulsive time of impact equals 0.30 seconds. Front impact. For front impact analysis, we assume the vehicle is going in the forward direction and it suddenly strikes a rigid obstacle like a wall with a maximum speed, i.e. 45 km per hour, and comes into rest after the collision. Then the impact force F will be. The impact forces were applied on the forward part of the vehicle, and the rear suspension points were constrained to restrict all of the 6 degrees of freedom. Rear and side impact. For rear and side impact analysis, it was assumed that some other vehicle comes and strikes with our vehicle. In this case, the impact will be of the second type, that is the impact of the roll cage with a deformable body, so the impact time will be 0.30 seconds. Then the impact force F will be rollover. As we know that the chances of having a rollover are more than that of the front, rear, or side impacts, in adverse off-road conditions, so to analyze the vehicle against a rollover condition becomes crucial. We have to analyze the vehicle in the worst condition which it can experience at the event, and that is when the vehicle falls upside down from a height, let us say 1 meter. Then from the law of conservation of energy. Time taken was 0.15 seconds, as the ground is considered a rigid boundary. The impact force is applied at the joint of row and FBM members at an angle of 45 degrees, with the vertical and lower part of the roll cage being constrained. Row roll hoop overhead member. FBM front bracing members. Torsional rigidity. Torsional analysis of the roll cage is carried out to determine the torsional stiffness to withstand off-road conditions while taking into consideration the torsional forces acting on the frontal and rear members of the vehicle. Both tires on the front and rear axle experience a moment. The torque is applied to one tire and reacted by the other one, which is equal and opposite, hence a couple is generated which tries to twist the roll cage. Steering knuckle. The steering knuckle is a very vital component that integrates the wheel assembly, that includes the steering, suspension, and brakes, and is connected to the frame with the help of suspension arms. It also plays a very important role in the steering mechanism by using the linear motion of the tie rod to give a turning effect to the wheel's assembly, following Ackermann geometry. Designing of knuckle was a complex task as it is included in unsprung mass, so it has to be lightweight and also it has to withstand various forces in off-road conditions, so we had to design the knuckle in such a way that it would give the best strength to mass ratio. The complete design process of knuckle can be divided into following steps. 1. Basic designing of knuckle according to suspension hardpoints. 2. Calculation of forces in different boundary conditions. 3. Analysis of knuckle. 4. Topology optimization of analyzed knuckle. 5. Final designing according to optimized data. 6. Analysis of final knuckle. A. Basic designing. The basic design of the knuckle was made considering a. Suspension hardpoints. The location of suspension points was calculated with the help of Lotus suspension analysis software with the following wheel alignment parameters at static. B. Weight of the knuckle. Weight of the knuckle is very crucial as it adds up to the unsprung mass of the vehicle, so the design must give sufficient strength with the least possible weight. C. Material to be used. Material selection is also a very important parameter. It defines the volume of the design and also the weight according to the strength of the material. D. Machining process adopted. Design is very much influenced by the available machining processes. E. Cost. Along with the machining process, the cost is also a major constraint at the time of designing, as it influences many other parameters like material selection, machining process, accuracy in fabrication, etc. Firstly, the suspension hardpoints along with wheel center point and outer track rod ball joint were plotted with their respective coordinates in a space of SolidWorks. The next step was to locate the distance of brake caliper mounting from the wheel center, which depends on the positions of the hub and brake rotor and also on the distance between both the holes of the brake caliper. Now we have all the required points for designing the knuckle, so designing starts with the main body that connects the lower wishbone outer ball joint to the upper wishbone outer ball joint, and then the steering arm and caliper mountings are added onto it. After some finishing works and reducing the sharp edges with the help of fillets and other features, basic design looks like this. B. Calculation of forces. For calculating the forces acting on the knuckle in adverse conditions, we have considered a situation when effects of a bump, cornering, steering, and braking are acting at the same time. The forces in each case were calculated separately. Force calculation due to a bump. We have considered a case when the vehicle goes over a bump and the wheel reaches its maximum travel in this position, the damper compresses completely and suspension arms rotate to their maximum. In that instant we can assume the whole assembly to be in static equilibrium. We have used Fox Float 3 and referred to its manual for calculating force at maximum compression, which is 5,700 N for 4 inches of longitudinal travel. Now with the help of suspension hardpoints, we made two sketches of lower suspension arm assembly, one for the vehicle in a static position and another for the above described position. Distances and angles from the front view are shown in Fig. We can see that the angle between Fox and suspension arms at extreme conditions is 51 degrees. All the horizontal force on the ball joints is assumed to be acting due to cornering force only. Let Fc be the total cornering force acting on one wheel of the front turning with a velocity of v equals 45 km per hour or 11.12 m/s and with a turning radius of r equals 2.5 m. Then This force will be acting on the spindle that passes through the wheel center, therefore by considering static equilibrium condition we can calculate the value of the forces acting on both the ball joints. Let the force on lower ball joint in horizontal direction be, FLB, H, and that on upper ball joint be, FUB, H. Then, from moment conservation about lower ball joint. Calculation of forces on steering arm. The steering axis intersects the ground at some distance from the point of contact of the wheel. This distance is equal to the vector addition of scrub radius and caster trail. Due to this separation, the net frictional force causes a moment about the steering axis, and this moment is balanced by a force acting on the steering arm of the knuckle. Wheel and ground were assumed to be a point contact pair with the patch area 0. Two frictional forces are acting on the wheel in the described boundary conditions. One is cornering frictional force and the other is trailing frictional force, hence there are two moments caused by each force, with cornering frictional force and caster trail causing a clockwise moment and trailing frictional force and scrub radius causing an anti-clockwise moment. See analysis of knuckle. After basic designing and calculation of forces, now this was the time to analyze the design in calculated boundary conditions. Spindle and knuckle were analyzed separately. In this segment we will be discussing the analysis of knuckle only. The purpose of the analysis is to make sure the designed knuckle withstands the calculated forces with an appreciable factor of safety. Since the knuckle is a three-dimensional object, we need to have 3D mesh elements inside the volume, and therefore we have used three-dimensional hex-dominant mesh elements of second order with a mesh size of 2 mm and with free face mesh type being quad/tri. Sharp corners and edges and curved surfaces are the locations which are very likely to have maximum stress concentration, and therefore it becomes very important to have a good quality mesh in these areas. To fulfill this purpose we have used certain mesh features provided in ANSYS Mechanical. A. Mesh defeaturing. Small corners can deviate the results by having maximum stress concentration. To avoid this deviation, mesh defeaturing is used. It defeatures or removes small corners. The value of mesh defeaturing taken was 0.4 mm. B. Capture curvature. To capture small curves and to have good quality mesh at curvature. The minimum curvature size taken was 0.5 mm. C. Capture proximity. This is the most important feature. It captures all proximities and helps to generate a small and good quality mesh in these areas. The minimum proximity size taken was 0.5 mm. 1. Forces on lower ball joint. FLB, V equals 2660.76 N in vertically downward direction, B. FLB, H equals 1389.58 N in a horizontal direction towards the wheel center, C. 2. Forces on upper ball joint. FUB, H equals 1281.34 N in a horizontal direction towards the wheel center. 3. Force on steering arm. 618.69 N in a horizontal direction towards the wheel center. 4. Moment on caliper mounting. A moment of 43,910.73 Nm in clockwise direction. The results of the analysis. D. Topology optimization. Topology optimization ensures that the designed part doesn't weigh more than required without any compromise in the factor of safety. Any extra material adds up to cost of manufacturing as well as unsprung mass, and due to the extra material loads on moving parts are higher than necessary, and hence energy efficiency is also being compromised. We can see that there are some areas where the amount of material is more than necessary and there is a scope of material reduction in those areas. Final designing. The final design of the knuckle was made based on results obtained from topology optimization. The area of interests was the upper part of the knuckle, caliper mounting and steering arm. Analysis of final knuckle. The final design was verified under the same boundary conditions. The results were satisfactory as there is no change in deformation and also stress is in the permissible range with a safety factor of more than 1.7. 6. Suspension arms. The selection of suspension geometry is done to fulfill our requirements with the minimum material application. A double wishbone with dual A-arm, with a damper to lower wishbone is chosen for the front as it has the advantage of more variation in toe angle, camber angle, and caster angle. For rear H-arm with camber link arm is selected due to its robust structure and lesser material requirement and fulfillment of requirements of rear suspension geometry. To satisfy our wheel alignment parameters, the coordinates of the control arms were located using Lotus suspension analysis software for appropriate length and dimensions. For the selection of appropriate thickness of the control arms we used bending equation. Considering pure bending. Force due to Fox on maximum compression equals 5700 N. Vertical component equals 5700 sin, 51. Therefore thickness equals, d/2 equals 2.9 millimeters. The minimum requirement of thickness is 2.9 millimeters and hence we used a pipe of external dia 1 inch with a thickness of 3 millimeters. The control arms were designed and then simulated with extreme boundary conditions. A force of 5700 N was applied at the suspension link at an angle of 51 degrees with both inner and outer pivot point constrained. 7 results. Frame, maximum stresses, von Mises stress, and max deformation in all the impact tests of the designed frame are in acceptable range with a good safety factor. 8. Conclusion. This paper summarizes ways for calculations, optimization, and economic as well as ergonomic designing of a light ATV with maximum possible safety factor under extreme boundary conditions. The impact analysis of the roll cage, structural and topological analysis of steering knuckle, suspension arms are well illustrated above. Acknowledgement. We would like to thank our seniors, professors, and college administration for their guidance and support throughout our career. We would also like to thank our teammates for successfully helping to complete the designing and manufacturing of the ATV. Lastly, we want to thank our family and friends for motivating us to be part of the project and to write this paper.